only this usually does not work well, because this selection of a student, it's very subjective. So the professors would like to select students who have something more than others. So when people from or students from all over the world are applying, and there is no clear benchmark to decide who is a better student, we have to be careful about some more things. So for that, one of the basic thing is like we should contact the professor directly. So this is like a sample application, like you send an email to your professor. So you have to find the professor who is working in an area that you are interested in. Then you can give a brief background about yourself, whether you're a bachelor student or master student.
Dr. Sadeed, may I interfere here?
Yeah, sure.
Yeah, please on your presentation once more. So it's been gone, I think. Yeah.
Can you see right now?
Yeah, let it be. Can you do once more the present?
Okay, sure.
Yeah, now it's okay.
Okay, so I'll start from here.
Yeah.
So okay, so this is a slide after the video, and so what I was saying is like you can find the website for the desired university which you are trying to apply, and you can see the place where you have to give your details and the background. And that you have to do anyway, but after that you can send an email to the professor which you feel like he's working in a field that you can perform well. Then send an email. You don't have to give a lot of details. You can give a brief background, like you are a bachelor student or a master student. And you can mention like you are from India, because professors usually like Indian students. So mentioning you are from India, it boosts your chances. Then, of course, you need to have prepared a good CV. And sometimes they ask for a statement of purpose. So statement of purpose is like a 1-page or 2-page letter that describes like why you want to work under that professor. So you send this email, provide your CV and statement of purpose along with this one, and then just wait for the response. So this is what boosts your chances. But one of the mistakes which students do is like they prepare one email and send the same email by changing the name of professor to all the professors which they are interested. So that in a sense does not work well, because these professors, they usually get this kind of emails maybe 10 to 100 like every day. So those many students are like eager to join for that professor. So if a professor finds like it is a general email, like the student has just prepared one email and sending to everyone, he usually ignore it. But if they find like this guy has spent time on his research background and he's really interested, that is when they actually go to your CV and look for your statement of purpose and other things. So so my advice is like never send a general email to a professor. You have to do some homework. You spend some time with the what the professor is doing. So you always have a website for a professor. So you can find like what he's doing and then prepare the email and send. So the professor should feel that this guy is really interested to join that group. Then some more things I will add towards the end. So with this background, I'll start with computational physics. So computational physics, if you want to like describe it, it is like using computers to solve real life problems. For some problems, we can use our desktop computer or laptop, but if it is a really big problem, we have to use supercomputer. So I'll first introduce what is supercomputer, then move on with computational physics. So for a supercomputer, as an example, if we are thinking about a guy who is building a wall, so he's building a wall around a small area or something. So like in a couple of days or weeks, he would be able to finish this wall. But let's see if somebody wants to build something like this one, Wall of China. So in this case, if you just have one guy who is trying to build this one, of course, he won't be able to finish it in real time. So of course, the solution is to use a lot of people. And so there are a lot of people who are actually building the wall and some others who are managing these people. So you need a system that takes care of this process. So by this one, basically what we are doing is like instead of one person, we have a lot of guys who are working for the same purpose and finally coming with a result. So supercomputer is similar. So we have a small computer that can do some jobs. But when we want a very big problem, what we do is like we combine this small computer using some connections and other things. So we connect maybe 10,000 or 50,000 computers and make a system, very big system as shown here. So this one is going to be very fast. So if you want to solve a problem, for example, if you give a problem and hopefully most of the time if the problem is big, the computer won't be able to solve like whatever time you give, but just give like hopefully it is going to solve in 10 years. So the same problem, if we give to supercomputer, it can take like 2 hours. So you see the difference, like you get the same result in 2 hours. So if you want to really do some real jobs, you need this kind of speed. So that's why we use supercomputer to perform most of the problems in computational physics. Now I will go to the some of the applications where we use this computational physics. So for example, we have aerodynamic simulation. So basically it means like you are studying the flow of something, usually air or water or some other fluid in a system. And these aerodynamic simulations or aerodynamic analysis, they use some equations. So those you first start with some physical equations and use these equations in a supercomputer to solve. So the applications are shown here are like one is like city planning, even though it is not common in India, like places like in Tokyo or something. If you are going to build a new tower, like a tall tower, they actually use computer and study like how this building is going to affect wind flow around that area. So like people use it for planning the city. Also, it is used in sports to design your balls, bats, or something like to make sure like it gives the best performance. And it's also used in automobile industry to make sure like the airflow is smooth, like it does not have much disturbance. And as the last example, I have shown like aircraft design. So in all of these examples, maybe the most important thing is aircraft design. So using this aerodynamic simulation, we are able to design like more optimum aircrafts. So I'm just giving an example like what happens if you simulate the aerodynamics study for an aircraft. So you can see like the computer using the supercomputer, you are able to study how the wind flows when this aircraft is flying. Of course, in this example, the turbines are not rotating, but they can add that too. But just as an example, we can see this. So we can know like if the airflow is smooth or if there is some disturbance that can cause a danger to this flight. All these things can be analyzed in computer. So this helps a lot because if you are going to design an aircraft and then find out like its design is not optimum for a safe travel, that costs a lot of money. So here the cost is like the supercomputer or running the supercomputer, which is electricity. So even though it is not that cheap to run a supercomputer, it is much cheaper than actually building an aircraft and testing the safety of that. Professor Nishad, can you see this slide now?
Yeah, it's visible.
Okay, thank you. So another example is thermal analysis. So to make it simple, like how the heat flows in an object. So this is also a very important field of engineering. So as shown some examples like gearbox and a vehicle, or in chip, if you are running a computer or something, you will know that the CPU or the motherboard, it heats up if you are running the system. So the design has to be optimum to make sure there is no overheating in the system. So these things can be studied in a computer before actually manufacturing this your computer. Also, this is also used in weather forecast, and you can actually predict like how will be the temperature tomorrow or day after tomorrow by solving a thermal analysis problem in supercomputer. Then another example which I am using is electromagnetic analysis. Maybe people are not much familiar with electromagnetics, but basically it's you can assume like it's something related with radiation of fields. And performing this electromagnetic analysis using a computer, it has wide applications. For example, biomedical applications, like if you are doing some radiation study of a patient or something, before actually performing the radiation on the patient, you can study it on the computer and make sure like the patient will not be harmed by your radiation. Also, it can be used in energy harvesting, or like if you are designing a new photocells or something, you can use this analysis. And as before, like in the previous slide, I have shown the thermal analysis on the chip. So along with thermal analysis, we have to also perform the electromagnetic analysis of chips to make sure like when you have a lot of components on a chip, maybe the components work very well when they are independent, but when they come close, one can radiate some fields that is going to affect the performance of some other part of the system. So these things, there is no clear way of finding a solution. Either you have to actually make the system and study, or else use this simulation and find out like if you place two systems nearby, they are going to perform poorly. Then it can be also used in, say, Wi-Fi analysis or something, and also for designing antennas and radar systems. So all these are like applications of electromagnetic analysis. So these are like background, like I'm just giving some applications where computational physics is used. And this is an example of the wave propagation when you have a lens. So on the left side, the source for generating the fields is at the center. On the right figure, it's moved slightly up, and you can see like the wave propagation is different in these two examples. Now I'll come to the part that is the theory behind this computational physics. So if there is a physical phenomena which we want to study, we start with some experiments on the study and then come up with a theory. So that is how traditionally people do it. So you come up with a theory, and in order to validate the theory, you again design some more experiments and try to predict the outcome. So if the predicted outcome and the real outcome match, then you have more confidence in your theory. So this is how traditionally science evolved, but now with the advancements in the computation, now we can also add the computer to the study. So what the computer does is like, in order to replace the experiment, now you can have simulations and perform the analysis of the theory. So this one helps in many ways. One is like you can repeat this experiment in a lot of times, but the other one, maybe it costs a lot of time to even set up the experiment. So repeating it maybe 10 or 20 times is like too much expensive. And some other times the experiment itself will be destructive. So like it is going to destruct something. So if you want to do it many times, that is going to cost a lot. Some other times it may not be even feasible to perform the experiment. For example, if you think of some gravitational study, and you want to study the gravitational interaction between two objects, and ideally you should have a setup where you don't have any gravitational interaction from anything else. So those things are not possible because we know like the gravitational fields are everywhere. So you cannot study only two objects, the gravitational interaction between only two objects in the real world. So those things you can actually study using simulation. So so you have a lot of different cases where we need computational physics to help to build your theory and find the physical phenomena behind that. So now, like old days, we have theory and experiment, like two pillars that were supporting the science. Now we can also add computational physics as a third pillar that is supporting the science. And very recently, this one has one more pillar, that is data mining. To be simplistic, we can assume like if somebody else has performed an experiment and you have access to that data, then you don't have to perform the experiment yourself. So so if there are a lot of data regarding some experiment, you can use that along with computational physics to build your theory. So now I'll give a brief description like what exactly we need in computational physics. So one thing what we need is accuracy. So if you get a simulation result which is very different from real world result, then the simulation is of no use. So the results should be accurate. So we have to be careful in building our system so that there is no place that is going to add inaccuracy. So for example, we have systems with a lot of components. So you have to make sure like when we interact the components, it should respect the physics of the problem. And when we are working with computer, maybe it may not be obvious for everyone, but computer has a limited accuracy for representing numbers. It cannot represent numbers to infinite accuracy. So we call it like it's like a precision error. So what we call is like usually we use 16 bits or something to represent number. But in the real world, the values are not limited to 16 bits or 16 digits. So they can take any value. So by limiting the precision of the numbers, that the final outcome of your simulation can be wrong. So we have to always respect this limitation and design your simulation result. The next thing what we have to be careful is the efficiency. we cannot design a simulation setup that takes a lot of time, that takes maybe more time than a real experiment to give the results, so that will not be much useful. The simulation should be fast, like as fast as possible, and especially in many of the examples that I have shown before, it deals with billions of unknowns. And solving a system with billions of unknowns, even in supercomputer, it is going to take time. So, but we can model our algorithm so that it is going to improve the speed of your simulation. We have to be careful about the efficiency. And the other thing is, like, whenever we design a simulation, we are not going to use it for just one time. We are going to run it for many times. So if the simulation is inefficient, that is going to cost a lot in this part. Now I'll start with an example. So I'm using electromagnetic simulation as an example to describe like how we actually get a simulation. So electromagnetic waves in one dimension, they can be represented like this. So we have a partial derivative of x, which is like spatial derivative of E is related to the partial derivative of time of B. And this E and B, they represent electric fields and magnetic fields. So combining electric fields and magnetic fields, we get the electromagnetic waves. So the equation on the left side, it has spatial derivative of electric field relating to the temporal derivative of the magnetic field. And on the equation on the right side, we have the other way. The spatial derivative of the magnetic field is related to the temporal derivative of electric field. So these equations, they represent electromagnetic waves in one dimension, and the constants are related to speed of light in this problem. So if you want to solve this problem using a computer, we start with a theorem that's called sampling theorem. So basically, if you start with a variable y that depends on x, so the red one is the function which varies around x, and sampling theorem, what it does is, like, instead of taking all the values of y and x, it selects some particular x values in the x-axis. And usually we use same distance between these samples of x. So in this example, the value h represents the distance between these x values. So denoting the first value as x0, the next value we can denote as x1, which is h distance away from x0. Then you have x2, x3, like that. So for all these values, you can find the value of y corresponding to these x values. So you have, like, for x0, you have f of x0, and for x0, you have f of x0. For x1, you have f of x1, and like that. So basically, this continuous problem now becomes a table like this, where you have on the first column, you have values of x, and on the second column, you have the values of y corresponding to these x values. Now, in the previous equation, we had derivatives. So if you want to take a spatial derivative, what we do is, like, at any place n, we take the next sample and subtract the current sample, and then divide with the spatial difference between the x values, that is h. So this gives the spatial derivative of x. Then similarly, we want the temporal derivative, so we can do it similar thing in time. So you take the next sample, like the future sample, and subtract the current sample, then divide with the distance or the gap in your time. So these two are going to represent your the spatial derivative and temporal derivative. Now, what we do is, like, where there is spatial derivative, we use this equation, And when there is a temporal derivative, we can use the other equation to replace this equation. Now the problem has become some equations which are linear equations on.
Excuse me, sir.
Yes.
Sir, the term you used for time derivative, can you please repeat?
Yeah, sure. So
I just want to know that name for that you used for time derivative, temporal, something like that. Can you please tell the term?
Oh, you mean temporal derivative? I'm not
yeah,
sure.
yeah. Thank you.
Oh, okay, sure. So yeah, like I was here. So when you are taking a derivative in time, wherever there was a derivative, you can substitute this equation. So that eventually the two continuous equations, they become a set of linear equations on f of x and f of t. And now we can substitute this in the equation. So you have a lot of variables which corresponds to all the x values, their f of x values, and in time also you have all the samples in time and corresponding the values of f of t. This eventually gives you a metric system like this. So what you have is on the left side, you have a big matrix that represents the interaction between your samples in x and time, and that is multiplied with the unknown sample values like x1, x2, x3 like this. And that is related to, on the right hand side, you have some known values. Usually this known values depends on the problem. For example, if it is electromagnetic waves that is radiating from a body, the right hand side vector depends on the geometry that is radiating this one, that is radiating. So once you have a matrix, you can use a matrix solver and obtain the solution. That means you are going to have, you can invert and get the values of f of x1 to all the unknown values that is going to represent the unknown solution which you are looking for. So one additional thing is in these problems, the diagram below, it shows like a real example how this matrix will be. So the dots represent non-zero values. So when there is white between, that is going to be zeros. So what we see is a very very sparse matrix. So even though its length and breadth are like very high, which can even go to millions or billions, the non-zero values inside the matrix will be very few. So if we use a normal inversion, that is actually a poor design, because there are a lot of zeros in the system which we are not exploiting. So designing an inversion for the problem, that itself is a research area. So that is something that's related to applied mathematicians. They will find out like how we are going to invert a matrix equation. But anyway, once you have the matrix and you have some inverter, you can in theory you can get the solution. So if you can invert it. So this is how we get the solution for this the problems of computational physics. So this is like started with the one-dimensional equation. So when we add dimensions, so the function is going to depend on x, y, and z, and the partial derivatives will be having derivatives along x, y, and z direction. But it's kind of extension, but that's still going to make your problem more difficult to solve, but it's still possible. So this is how we got the previous results. But I have to mention, like, this is just one way of converting a real world problem to a computer problem, that is like real world problem to a matrix equation. But there are more accurate and better ways of converting equations. But this is like a basic introduction. Now I will move to an application that I'm working on based on this kind of solvers. So this application is for simulating transcranial electric stimulation. This one, what we are doing is like we have a patient or a healthy person who is under study, and we place some electrodes and pass a very small current. So this current is going to interact with the neurons inside the brain. So of course, if the current is very high, it is very harmful, but these currents are like milliampere or something that's not harmful, but they can help in exciting some of the neurons and improve the condition of the patient or something. And these things are like a field that is under development. Like some of the countries allow this kind of treatment. Some of the countries are like, they still don't allow this for patients, but they allow this for research. So this are proven to be able to treat like some kind of depression, and it can also help in cognitive enhancement for some cases. I'll show an example of this one in the coming slides. And this is also like people are studying like how it can help if a patient is suffering from some memory issues like Parkinson's or Alzheimer's or something like that. So all these are like possible applications of this treatment. So this treatment, even though it is very promising, it comes with a lot of challenges. So what I am showing is an example where, say, a student or a person, he has some difficulty in learning, or especially in reading and grasping the ideas. So for that, we have to excite some of the parts inside the brain using this method. So this reading, the parts that are related to reading in the brain are shown here. One is called dorsal pathway and other is called ventral pathway. Both of them are for help, like they're exciting the neurons that are related to reading, but the purpose of the neurons are very different. So if a person has a disability, it would be disability maybe from only one side. So if a patient comes with this kind of problems, we have to excite one part without affecting the other part. So for that, we have to like design like how we are going to place the electrodes on the head, as shown before, and then how much current we are going to pass for that patient. And this thing, there is no standard solution for this one. It is going to vary from one person to another, because the brain, the head size is going to differ from person to person, and even the electrical properties of the tissue is going to vary. So due to all this, even though the doctor knows the solution for one patient, he may not know for a new patient. So he has to find out like which way we can help that patient. So for that, we can use the previous computational physics, especially the simulation of electromagnetic radiations, and find out like what is the best way to place the electrodes. So we did this study on a person, on a given data of a person. So we are given with MRI data for MRI data of head of a person, and what we are asked is like find the best possible ways to give the electrodes and the current so that we excite only one part. So we did a study, and we are showing here only the results. So on the left side, what you have is like the solution. We came up with two electrodes. So you can see a red circle and a white circle. And our aim is to excite the red circle with minimum effect on the blue circle. But they are very nearby, so it is very challenging. But we are still able to do a decent job with two electrodes. So the red one corresponds to high electric fields, which are going to stimulate that part. and blue corresponds to low electric field. So what we see on the left side is like inside the red circle, you have high electric fields, and in the white circle, you have relatively less electric fields. Now on the right side, the same result is obtained. Now we are using 4 electrodes. So with using 4 electrodes, we are able to obtain a bit more optimum result compared to 2 electrodes by exciting more in the red circle and less in the white circle. So this is all these tests are performed, like we have to run a lot of simulations and find out an optimal solution. But when we have access to supercomputers, it is possible. With this one, I conclude my introduction to computational physics, and as a concluding remark, like people who are interested to apply for my university, which is my current university, like if they are master students or something, they have an opportunity to write GATE exam in India, and the GATE exam is used as a valid exam for the application in my university. So like I have many friends who like based on the GATE score, they were able to get admission in my university. Like my university is not unique, like there are a lot of other universities which are abroad, like which are outside India, who still use GATE as a reference for admission. So you can check that in the GATE website or something. So this one I'll conclude with giving a video on my university. Action. Okay, that concludes my talk. I'm not sure if you are able to see the screen, but that was my last slide. So yeah, I just stopped a bit before, then I'll allocate a time. Now I'm open to questions or any queries or suggestions you have for me.
Hello, sir, can I interfere once?
Yes.
Hello. Yeah, there is a form there.
Okay.
So please, I'm asking to all participants, please do register and give a feedback so that we'll send the certificate to your email ID. Also, please do. My request to all participants, which is in the chat box. Yeah, please move to the question and answer session.
So I'm not sure if you're able to see my screen now, or should I share again? or if somebody like if some students are like they want to know the admission for some particular field or some particular university, if I am aware, I'm happy to help them, so they can ask that too.
Yeah. Neetu madam, yeah, please we'll share the link to you once. If there is any question, please you can ask the expert, so we can have a discussion. And in between, you just please.
Okay. So I just have to point out, like when I come to Kerala and some colleges, it's mostly like girls' college. Like most of the students would be girls, and I guess like girls may not be that eager to go outside, but I can ensure like these places are very safe for ladies. Like
no, sir, we have the participants not only from the Kerala. We have all over.
okay.
We have the participants from all over India itself right now.
Yeah, like yeah. Okay. So I'm just like giving like feedback, like even.
Sir.
Yes.
Sir, I am an alumni of Department of Physics.
Okay.
So I am doing my masters in Islamic Studies in
Okay.
CS Institute, Malappuram.
Okay.
So you were telling about the KAUST, right? King Abdul University.
Yes. Yes.
So you were saying about for if we are interested in a PhD, we can send email for the professors personally.
Yes, but that's okay. That's like that is an extra thing that you have to do.
So I was interested to know about the doing masters in physics at KAUST.
Okay, yeah. So they don't have any bachelor degree. They start with master degree. But usually their policy is like if you already have a master degree, like they may not consider, like it's not like a strict rule, but they prefer students who do not have master degree.
No, sir. Actually, I had my degree with physics, and
Okay.
I would like to pursue that side.
Okay, sure. Yeah, so the procedure is same like what I give you here. Is like you go to the university and apply it. Then even though it is master degree, it's still like you are going to be under some professor. So the system, this cost system is like what they assume is like if you come as a master student, you eventually be going for PhD. Like even though it's like you can always stop with master degree, but you will be working under a professor. Like a professor will be guiding you like which are courses you have to take and other things. So you have to find a professor who likes you, and yeah, when they like you, what it means is like they like to take you as a master student and then continue it for PhD. So the process of like sending an email is still like a good idea.
Sir, is there any preference for natives from Western countries?
As such, usually any university in a country, they will have some reservation for the students from that country. For example, my university is in Saudi Arabia, so they have some preference for Saudi students. But apart from that, they will not have much preference. But what they do is like they usually make sure like students from all over the world come. So like not only Indian students are coming or something like that. So they try to distribute the students among all the countries.
Sir, are they giving any kind of scholarships?
Yes, yeah, sure. All of them, they give good scholarship. Like
so the eligibility will be based on any kind of entrance exam or our marks?
Usually, no. Like these people, they don't have an entrance exam. Like they check your score in your bachelor degree or something, and like if a student is able to like publish some paper, that gives a very good chance of getting admission. But usually, I think like students in bachelor degree, they don't publish much. But your score and like your email also makes a difference. Like you have to show like you are really interested to work under that professor. Like you are not looking for any professor.
So if we have published a number of research papers in a particular area that we will
Yeah, yeah,
like to focus, then
that gives a very good chance of admission, because like publishing a paper is like the most valued thing in research.
okay, thank you very much, sir. Thank you.
Welcome.
Well, is there any other question, please? Well, in between, just please go through that link for the feedback, and please do register your name and email ID properly. So the email ID you have provided here, there we will send your certificates. Sadeed, Dr. Sadeed, I hope it is fine. And
Okay.
there is no more questions right now.
Okay, sure. So once again, thank you for giving me an opportunity.
Yeah. We have a vote of thanks right now. I think Sumia. Sumia is there? Hello, Sumia.
Yes, sir. Yes, I can hear.
Yeah. Please, yeah. Over to Sumia, madam, for the vote of thanks.
Okay, sir. On behalf of the Physics Department and MES College, I express my heartfelt gratitude to Dr. Sadeed sir for conducting such a wonderful session. The session was really informative and inspiring, and I do feel confident that most of the students who have attended this session is inspired to study abroad. So thank you, sir, once again. Thank you, everyone who has attended the session.
Okay.
Thank you.
Well, thank you all on behalf of Department of Physics. And please do register on that particular link so that your certificate will be generated.
Okay, thank you, everyone.
Thank you, Dr. Sadeed.
See you. Bye.